All right, everybody, here we go. I'm going to go over just a few things that we talked about in class the other day when we introduced the polar forms of conics and eccentricity. And then we're just going to do a few more examples, and that will be it for this video. So I wrote down already what we talked about in class. So here is a sketch of a conic, and I need you to keep in mind that it can be any conic, right? This is not just a parabola because you just see a little piece of it. It could be an ellipse, it could be a circle for that matter, it could be a hyperbola, it could be any conic. This will be true for all of them. Okay, so what is the definition of eccentricity? Eccentricity is usually, no, not usually, it's always written as a lowercase e, not to be confused with Euler's number e, right? This is not Euler's number e 2.718, etc., etc. And e is never negative also, by the way. So this little e stands for eccentricity. And what is it? It is the ratio of the distance from a point P. So if you're looking here, there is my point P, right? So ratio of the distance from point P to the focus, so that's this distance, over the distance from that same point P to the directrix. So it's a ratio of those two distances, and not just in any order. The distance from the point to the focus over the distance from the point to the directrix. That ratio is what E is. Okay, and also for further not use in our examples, it's also C over A, and those C and A come from our Pythagorean identities that we have studied in all the different equations of conic sections that we have looked at. Okay, all right, so the point P is, sorry, the point capital F here is your focus, and the focus is always located on the pole in the polar coordinate or in the polar form of a conic section, right? So we're always going to place the focus on the pole, which in the Cartesian plane, that will be the origin, right? There are those properties here that are going to be true for all of them. So the parabola is always going to have an E number or E value of 1. And when you're thinking about that, you should know that for parabolas, every point on the parabola is at the same distance from the focus than it is from the directrix, right? That means that the distance PF in a parabola is equal to the distance PD, and therefore if you put something over itself, that will give you a 1, right? So for parabola, E is always 1. And if you're thinking about it in that same fashion and you do a little sketch for yourself here, and you cannot try that on an ellipse and on a hyperbola and on a circle, you should see that for ellipse, E is always going to be between 0 and 1. Not inclusive, right? Cannot be 0, cannot be 1. Hyperbolas, E is always greater than 1, and for circles, E is equal to 0, actually. And that's because we're thinking about the limiting value there for the circles, kind of a special case there. All right, so this graph holds true. So I kind of reproduced a little sketch here for any conic, right? And I put a note on the right side there that this holds true for any conic, parabola, ellipses, hyperbolas, even circles. And therefore, the resulting polar equations that we're going to work out will be true for all the conics, which is really cool about that polar form of conic sections. It's that you have one equations for all of them. So it simplifies a lot of things. And it's with respect to an angle. So when we're doing rotation of those conics, that simplifies that as well, that process as well. Okay, so I want you to refer back to this sketch here. And then let me go here. Let's put down a few things that we see from that sketch, right? So what we see is that the distance PF is really my radius, right? So you're looking at my sketch, you see the radius of that triangle I drew here. So I drew a point on the conic section. I link that point to the focus, which is on the pole, right? And that makes this a radius here, a distance r, which is my distance pf. And then I drew that angle that goes from the polar axis to the segment that joins the focus to the point. Okay, you can see all of that on the sketch. From that, we determine that the distance pf is equal to r. Okay, that's one thing. And the other thing we can see from my sketch is that the distance PD is equal to, now this one might not be as obvious, so I'm going to help a little bit. So we're talking about this distance right here. The distance PD is equal to that distance D, right? Because this is my y-axis, so all the way to the directrix, that's the distance D, minus r cosine theta, right? That will be the short leg here, right? So PD is equal to D minus r cosine theta. So backtracking all of that. So PD is equal to D minus r cosine theta. And refer back to the sketch for all of that. Now we're going to put all of that into our equation that we talked about earlier. This equation for eccentricity. We're going to first rewrite that. So we're going to rewrite it without a fraction. So I'm going to say PF, the distance PF from the point to the focus is equal to E times the distance from the point to the directrix. And now that I have that like that as an equation, I'm going to replace PF with R. So PF is R. So R equals E times, and then PD I'm going to replace by D minus R cosine theta. Okay? Now that I have that, I'm going to isolate the R. So to do this, I'm going to distribute that E first. So R is equal to ED minus ER cosine theta. Now I'm going to add this term of ER cosine theta to both sides so that I have both R on the left of equal, so R plus ER cosine theta is equal to ED. And finally, I want, well, not finally yet, I want to get R by itself. So I'm going to, I have a R here and an R here. So I'm going to factor those out. So R factored out. So this R divided by R becomes a 1 plus E cosine theta, because this R is factored out, is equal to ED. And I'm sure you see it happening right now. Therefore, R is equal to ED 1 plus E cosine theta. And that's the equation for the polar equation for a conic that has the directrix, so the focus on the pole, and the directrix on the right, as a vertical line. So this will be for that. But we have 4 different scenarios, right? So I just showed you how we derived this. This is very important. But then the 4 scenarios. Here are the 4 different conics we could look at. First one is the one we just did, right? We have a, is that the one? Yes, that's the one we just did. We have the focus at the pole. Notice all 4 focus at the pole, right? The focus at the pole. The directrix is a vertical line on the right, in the positive area of those x's, right? So it's a positive, so plus here. And because we're going to be horizontally oriented for the conic section, this is going to be a cosine, okay? For the next one, the focus is at the pole, but the directrix is on the left of the focus. So therefore, we're going to have a minus here. My directrix is in the negative area of those x values. And because we're oriented horizontally, this is still going to be a cosine. The next one, the focus on the pole, but the directrix is above, so that's a plus. My directrix is in the positive area of the y's, and because we're now oriented vertically, we're going to have a sign here. And for that, I'll invite you to draw that the other way and redo all the thinking that we just did here all the way, and you see that you would end up with r is equal to ed over 1 plus e sine theta, because you would then need that side right of the right triangle as opposed to the other leg, right? Okay. And finally, we're going to have the focus at the origin, at the pole, sorry, and we are going to have a minus because the directrix is oriented in the negative area of that y-axis, and then we still are oriented vertically, so we still have a sign here, okay? All right. Now let's walk through a few examples. So example 1. We're going to find the polar equation. So find the polar equation for a parabola that has its focus, and we know where that should be, right? At the pole or origin, and whose directrix, almost the same one, not quite, whose directrix is the line y equals -6. Okay, now look back at our examples from up here. We have a y directrix, so it's going to be one of those two with a sign in it, and we have a y equals -6, so we know that we're going to be in the very last of our scenario here, and so we're going to have, that form of the equation to be, okay, let me change color so we see. Now I'm going to be working through. So that form that we are looking for is r is equal to ed over 1 minus, because we have that negative here, e sine theta. Okay, so we need to figure out e and d is really all we need, right, for that equation, which is pretty cool. Well, we know e because we're told this is a parabola, and earlier we discussed how parabolas have e value of 1, all of them, without exception. So we know, therefore, parabola, therefore, e equals 1. So we know that. And we have the directrix. So the directrix is a line y equals -6, therefore d is equal to 6, right? It's the absolute value of that. And therefore the equation is going to be r is equal to, so 1e times 6, right? So 6 times 1 is 6 over 1 minus e is 1, so there is our equation. Example 1 done. Example 2. We're going to find, so here we have to do a few things. So we're going to find eccentricity. We're going to identify the conic. So which one are we talking about? We're going to locate the directrix, and then finally we're going to sketch the whole thing, right? Okay, so well, we need to be given a polar equation. So here is my polar equation. R is equal to 10 over 3 minus 2 cosine theta. Okay, well, we already know we don't have a parabola, right? Because E is not 1. See how we have an E of 2 here? So we're going to know, so let's do that. So we already know E equals 2, and no, never mind, we don't know that. Ooh, 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 ooh. Don't do like I'm doing here. We don't know that. This is not a 1 right there. And see, all our forms of equation, they all have a 1 there. So we need to make that become a 1 first. So I need to divide everywhere by 3. So let's do that first. So divide everywhere by 3 will give me R equals 10 over 3. And then 3 divided by 3 is the one I want. And then this divided by 3 will be 2/3 cosine theta. All right, now I know my E. So E, let me move you a little bit. So now we know that E is equal to 2/3. Remember, not the negative, right? E is always positive, and that's between 0 and 1. Therefore, we know we have an ellipse. Okay, so we identified and we found the E. So we did the two first things. Eccentricity is 2/3, ellipse is the shape, conic. We need to locate the directrix. For that, we need D, and we know that ED is equal to 10/3, and we know E is 2/3, so we know that 2/3 D equals 10/3. Therefore, multiply through by 3/2, right? So D is equal to 5. Now that doesn't tell you that the directrix is at a positive x equals 5, right? It just tells you that the directrix is 5 away from the focus. So let's do a little sketch now. You're a little crooked, aren't you? You're a little crooked too. Yeah, I don't know if it's better, but we're going to leave it like that before I make it worse. Okay. So we have that. I know that the focus is going to be right there, right? We know that. And what else do we know? We know, well, we don't know much except that the directrix is 5 away. But we don't know where yet. I don't think we do. We don't know where yet. So let's do a little table. So we need theta and an R. And you know what R is, right? R is the equation we have been using. I don't want to deal with fractions, so I'm going to keep the original one. So that's the original one was 10 over 3 minus 2 cosine theta, right? Yes, okay. So we're going to use 0 angle 0, angle pi over 2 here, angle pi here, and angle 3 pi over 2 here, okay? So 0, pi over 2, pi, and 3 pi over 2. So when I go to 0, plug in a 0 in my equation here, so cosine of 0 is 1. So 2 times 1 is 2, 3 minus 2 is 1, 10 divided by 1 is 10. So at angle 0, which will be on the positive pole here, on the positive polar axis here, we're going to go 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that is the point 10, 0, right? In that form r theta, which we would for polar points, right? Okay, now I'm going to plug in a pi over 2 in cosine, that's 0. Therefore, I have 10 over 3, so that's just going to be 10 over 3, which is 3 1/3, right? So at my angle pi over 2, I'm going to go 1, 2, 3 1/3. Here we go. Then we are going to plug in a pi. Cosine of pi is a negative, so we have a 3 plus 2 is 5. 10 divided by 5 is 2. So when we are going all the way to angle pi, we're going to measure 2, which makes me be here. And you can kind of already see that shape, right? And then 3 pi over 2 is going to be 3 pi over 2. Cosine of 3 pi over 2 is 0. Therefore, I have a 10 over 3. 10 over 3. Now we have to be careful, right? We don't want to say this is that point again because we're going in the 3 pi over 2. So you're measuring your angle, 3 pi over 2, and then you measure down from the pole 3 1/3. And those are not the co-vertices, right? But they're the point on the poles there. So we're going to kind of looks like that. It's not the best ellipse, but it's not too bad. All right, but that also tells me now where my directrix will be, right? It's surely not going to be at 5 because that would go exactly through the ellipse, and that's not possible. So we're going to be at -5 here. So 1, 2, 3, 4, 5, and therefore the directrix is going to be right here at -5 for the x values there. I should say x equals, right? Because we're talking polars and then we're talking Cartesian plane. And I think we've done everything we were supposed to do. We found the eccentricity, identified the conic, and located the directrix and sketched it. There we go. All done. Next example. Example 3. Ooh. We're going to write a polar. Equation of a parabola with vertex 2 pi, and that will be r theta, right? 2 pi. Okay. All right, so let's do it. So we know we're dealing with a parabola. Therefore, we know E equals 1. And that's all we know, right? So then we're going to do a little sketch. And we're going to, of course, put the focus at the pole. And we want the vertex at 2 pi. So this is 0 pi over 2 pi 3 pi over 2. So when I measure my angle pi, I'm going to be here, and then 2 in that direction will take me right there. So the vertex is going to be right here. And I'm just going to go ahead and sketch that kind of this way. And we know it's a parabola, right? And because it is a parabola, the parabola has a particularity of having the focal length, which is the distance from the focus to the vertex, is going to be the same as the distance from the focus to the directrix, right? Those two distances have to be the same. Therefore, I know the directrix is going to have to be right here. And because this is a distance of 2, this will be at x equals -4. So the directrix is going to be right there. And therefore, d is equal to 4. Remember, d is going to be a positive value, right? It's a distance. And my goal was to write the polar equation for that. So I think I'm ready. We know E because we know it's a parabola. And now we know D, so we have all we need. R is equal to E times D will be 4 over. This is the directrix is on the left of the focus, so we do a minus, and it is oriented horizontally, right? So therefore it is a cosine. E is 1, so 1 times cosine theta. Those equations are so nice. So nice and easy. All right, last example. We are going to, so example, I forgot where we are. I think that's example 4 maybe. Check that. Yes, example 4. Okay, so we're going to sketch the conic. R equals 12 over 2 plus 4 sine theta. And we're going to write the equation in Cartesian form, which is the standard form for a conic. Okay? All right, so let's do it. First of all, we don't have a 1 here. That's not the way I want that equation, so I'm going to rewrite that, dividing by 2 everywhere. So 12 divided by 2 is 6. 1 divided by 2 is 1. 4 divided by 2 is 2, and then that's a sign. Okay, now I can deal with that because now I know that E is equal to 2, which is greater than 1. Therefore, I know I'm dealing with a hyperbola. And then 6 is equal to ED. And E is 2, so 6 is equal to 2 times D. Therefore, D is equal to 3. I know that I am oriented vertically, right? So the hyperbola looks this way because I have a sign here. And what else do I know? The directrix needs to be in the positive area of the y-axis. Okay, so let's see what we can do. Can we do a sketch already? focus is going to be on the pole as usual, right? And what did we say we knew? We knew the directrix was 3. How about we do a little table first, right? And here it doesn't matter which version of the equation you use because there are no fractions, right? So I can just use the simplest one, but it doesn't matter which one, they're the same. Okay, so I want 0, I want pi over 2, pi, and 3 pi over 2. So when I plug in a 0, sine of 0 is 0, so 6 over 1 is just 6. So when I do angle 0, I'm going to go out 6. So 1, 2, 3, 4, 5, 6, and I have a point right here. Pi over 2, sine of pi over 2 is 1, so 1 plus 2 is 3, 6 divided by 3 is 2. So when I go up pi over 2 for my angle, I'm going to go up 1, 2. And when I go pi, sine of pi is 0, so that's 6 again. So go all the way to pi and then 6 out. And 3 pi over 2, sine of 3 pi over 2 is negative 1, so that's 1 minus 2 will be negative 1. 6 divided by will be negative 6. But now remember, right, we're going to go turn, find your angle, 3 pi over 2, and then in the negative area, so we're going backwards from the pole. So 1, 2, 3, 4, 5, 6. Okay. So I can already say that this will be one of my vertex, right? So my one branch of my hyperbola would look like that. And then using the symmetry, I can say that my other branch would look like that. And so now I know that my directrix here, d equals 3, will be at y equals 3. So 1, 2, 3, there is 1, 2, 3, there is the directrix. Notice the directrix is not the center, right? Because there are really two directrices for a hyperbola, but the one we were given is this one at y equals 3. That's the one we know. And what else would I need to write an equation? Okay, so we graphed it, and that's pretty much all we would have to do, right? Sketch the conic, we just sketched it, but now we have to write the equation in Cartesian form. Okay, so what do we need? For Cartesian form, for a hyperbola oriented vertically, we need y minus k squared over a squared minus x minus h squared over b squared equals 1. Well, what I need hk, I need the center. Well, the center is exactly halfway between the two vertices, so it's this point right here, which is the point 0, 4. Therefore hk, so I know I need y minus k is 4. And a is the distance from the center to the vertex. So, oops, stay here. A will be that distance here, which is 2, right? So a equals 2. And I want that squared, so that's over 2 squared, which is 4, minus h is 0, so that's just going to be x squared, over, I need b squared here. I don't know what b is yet, so we need to figure that out, okay? And to figure out b, we need to go back to our Pythagorean identities for hyperbola. So that was c squared is equal to a squared plus b squared. And I want b squared, so really c squared minus a squared equals b squared. And I don't need to take a square root because I really do want that b squared at the bottom of my equations, right? So the c value is the distance from the focus to the center. So, oops, let's change color. So that will be that distance right there, and so that will be 4. So C is equal to 4. So we have 4 squared minus A, we said is 2, which will be equal to our B squared. So 16 minus 4 will be 12. And that's B squared, not B, but that's really what we want, right? We wanted B squared, remember? So this should be, I don't want my square there anymore. This should just be 12. And this is the equation in Cartesian form. All right, that's long enough for a video. Have a good rest of your day.